Hey, hello everyone. My name is Zack Akil. I'm a machine learning engineer and developer advocate at Google. And I also am the co-organizer of the Central London Data Science Meetup. How many of you have attended one of my meetups? Oh, damn, quite a few. Oh, there's a couple. Cool. No. So, can you all hear me from here? Yeah. Is this on? Okay, cool. A bit more about me. The things I like to do is build machine learning into applications. I was previously a software engineer, and then I started learning machine learning on like Coursera, and I always was interested in how could you actually get machine learning working in applications. The applications that I wanted them to get working in weren't necessarily business critical applications. The first one was this. So this is a physical neural network. So taking a scikit-learn model and training a neural network in that, and then showing the weights on like RGBs. So you can see like incredibly useful. Well, like when I first saw it, it was the first time I ever saw learning happening. So it was kind of cool to see. If I can show up the top, there's a little at the very start. There's like a bright activation over here, and it kind of moves. It kind of slides over to the right-hand side. Again, like I can't learn anything from it, but it kind of looks cool. The next application, or one of the more recent ones, was this. This really like set the tone for the kind of talk this might be if the Wi-Fi works. Okay, the Wi-Fi is as unreliable as predicted, as Marco mentioned. Okay, cool. So let's imagine nothing happened. The other thing I built was this bike that was for the PyData conference that happened 1 month ago, happened in the past. And what it did is it did object detection facing behind the bicycle. And then if there was, say, a dangerous object, it would light up the handlebars on the side of the handlebars where the danger existed. So you can see here, this is the output of the video. The video is flipped. So the bus is on the left, the car is on the right. So the bus is green and the car is red. And the size of the handlebar that it lights up on is representative of how close in the direction of the thing. So that one's like kind of useful. And if you're interested in that project, you should follow me on Twitter because I may or may not be working with a certain bike company to actually build this into a real bike. So I know, stay tuned for that. Okay, enough about me. What about you? So how many people in the room are data scientists? That's a lot of data scientists. How many people have done any kind of machine learning? Okay. How many people know what linear regression is? Okay, so if you don't know what linear regression is, I like to assume no knowledge. That's my style. I'll skip over this slide. But just in case you've forgotten what linear regression is, I'd like to show off this really cool tool, which linear regression, 2 variables. You change the 2 variables. I know, yeah. Change the 2 variables, and it changes the line. So, okay, now everyone knows what linear regression is. I want to highlight not just knowing what it is, knowing that we could use a line to predict something. I want to draw attention to the fact that not only can we predict the tabs are bothering me. Let me just Okay. Not only can you use a line to predict, but after you've learnt your line, you can maybe get some sort of insight from the coefficients that it's found. So in this case, I'm imagining I'm a farmer trying to predict the weight of pineapples based on their age. Again, very relatable. And the idea is that, although, yeah, we can make predictions using this line, but just by looking at the coefficient that it's found, we can kind of see that, okay, the weight goes up slightly slower than the age, and then when the age is 0, the pineapple weighs 5, whatever it weighs, kilograms, magic pineapples. But the idea is I want to sort of talk, because it might come back later in the talk, who knows. But we might talk about how we can use the coefficients that I've learned for insight rather than just using a line to make predictions. Okay, so basketball. Again, smooth transitions. I play a bit of sport, and I wanted to get out more, so someone suggested, oh, maybe you should try basketball, because there's a lot of basketball courts in London. And I went away, I bought a basketball, I went to the court, I tried to shoot. Anybody play basketball, by the way? couple people, yeah. I tried to shoot some hoops, as they say, and it was very hard. It's surprisingly difficult, even when you've got no opposition. So the idea is, I was getting bored quite quickly, and I wanted to do something. What I usually do is I'll do something, I'll get bored with it, and then I'll try to put some like sort of tech on it. Does anybody else do this? Well, they start thinking about apps that you could do to do with the thing that you're bored with. Yeah, it's kind of common. So that's the idea. So if I can't be good at it, can I look cool doing it? This is the idea. So rather than build an app, maybe do something artsy. So who's ever heard of long exposure photography? Who's done it? Has anybody done it? Yeah, so it's the idea that if you have done it or if you haven't, it's the idea that you can take a camera, usually quite an expensive camera, and rather than a camera just opening and closing the lens to take a photo, you can open the lens or open the shutter, leave it open, and then any kind of light that happens in the image gets kept, and so you get these kind of long trails of whatever you do. So the idea is, oh, if I could do this with the basketball shot, I might be able to get a really cool light, even if it misses. In fact, if it misses, it becomes a more interesting trail of light, so it's a win-win. So that was the idea. So I took the reflective tape that you get on cones, you can buy it on eBay for like £1, and wrapped it around the seam of the basketball. And I didn't have one of these cameras that could do the long exposure shot. All I had was my phone. And what was kind of important for the application using this reflective tape is that I needed a light source close to the camera for the reflection to come back and shine very bright. And fortunately, like most phones have a torch built in right next to the camera, so it was perfect. Just set it up, set it on video mode, and then make sure the torch is on, and you get the ball kind of lighting up nice and brightly in the night. And so the idea is I went out when it was a bit dark and shot some hoops. You can see I'm quite good. I got like 5 in a row already. And the idea is I would take this footage and I would pass it through some Python code and work out the trails, because I guess the light from the ball is a very distinct color in the frame. And so yeah, I went through. I actually used the Python package that I used was scikit video. So if you're ever working, has anybody used scikit video before? No one. Well, you should. Scikit video allows you to put in like an MP4 file, or I don't know if it works with AVI, but put in a video file, and it will take a video file and turn it into a big, long NumPy array. So it's very memory intensive. Here's the link. I've got these links littered throughout the entire talk, so if you're interested in the code used to produce this, you can like snap a shot of that. And I'll have all the links available at the end. So yeah, this is the shot. So here's the still of it. It doesn't look quite as cool as I initially planned. Like I didn't have the long glowing stream, mainly because like the frame rate of the video and the code I wrote was pretty like naive of just finding a distinct color, not putting in much of a threshold above or below. And you can see even like there's lights in the background because of the street lights. So it wasn't what I wanted. But then I thought, looking at it, it kind of looks like data. Yeah. So could I do something data related? So I thought to myself, if I can't look good at it, or if I'm not good at it and don't look cool doing it, the obvious next step, does anybody know what it is? That's right, do some machine learning. So the idea is I take this data and crop out the very interesting bit that looks like a kind of curve or a line, put it in some Jupyter notebooks, and then I'll try to do my linear regression. It didn't work. So a standard linear regression model won't work for this. I don't know if anyone was going to guess that, but that didn't work. But is there another line that does fit this? Like, do I know how to describe the line that I just shot? And the answer is yes. Wikipedia to the rescue. A trajectory equation should fit my data. And the idea is this equation that everybody knows. I've got a little animation or the thing before. So yeah, same exact principle. It's just a line with, when it loads, there it is. It's just a line with two variables. So an angle of the shot and the velocity of the shot. So it's almost identical to linear regression. And now the question is this the same as linear regression? Hands up who says this is the same as linear regression. Okay, hands up if this is called linear regression, if I try to fit this line. Hands up if it's called linear regression. Hands up if it's definitely not called linear regression. Okay. I also don't know. And I asked some people around the office this morning, data scientists in the office, they're also confused. So
I think it's a linear regression if you said that the axis are the angle and velocity.
if I set the axis to be the variables?
Yeah.
Oh. I don't know how that works. Anyway, we'll chat afterwards. But yeah, genuinely, I don't know. Is this still technically called linear regression? It's definitely regression still, but I don't know. But yeah, that's something to think about very thoroughly as I'm talking for the rest of the talk. So the idea is, yeah, we got this equation. And how can I do it? Well, I've got a notebook here. And the idea is I can code this equation. Fortunately, they don't have fit trajectory curve in scikit-learn. And they're not even in Keras either, so I have to code it up myself. And for that, I have a little notebook here.
If you inverse transform the data points before you did that, then Egypt would fit in line, right?
Maybe. We'll chat afterwards. Okay. All right, can everyone see that code? Yep. We'll go to the back. Cool. So what I'm doing here is I'm downloading the image of my data. I'm displaying it. Actually, I'll make sure I don't spoil the surprise by clearing all the outputs. Cool. So I'll display my data. So here's the cropped out data of the shot that I just made. I'm going to define the TensorFlow model. So in here I define, okay, what are the two variables that I'm going to be tweaking and changing to fit my data? Again, in that little animation I showed, I was tweaking and changing the angle and the force. So I'll declare those. Then I'll go down. Here's the description of the model. So here's the equation at the top. And all I'm doing here is I'm actually just writing it out in TensorFlow syntax. So you can actually see like the first part of this, the tan times x. That's just this first line, x times tf.tan. And then this equation is actually working in radians. So I've got a little function here that converts radians to degrees. And yeah, it's just writing out that equation in the TensorFlow code. I will run that. Okay, and then I will just show it. So here is my data alongside the default version of my TensorFlow code. Okay, so the red line is the model where it is, which it's quite far off the data. So what I can do that is like super cool is I can go in here and say, okay, force variable. There we go, force variable dot assign. There it is, super fast. And we're going to give it, I think it started at 50, let's give it 200. And we'll run the same cell. Oh, getting closer. All right, let's do the same for the angle variable. Here we go. Assign that to, what was it, started at like 40, let's give it 80. Oh, too high. I didn't know that was going to happen. Let's do 50. Okay, this is so hard to try to fit the variables to the thing. If only there was a way. So we have, in machine learning, we have optimizers. I don't know if data scientists are aware of optimization, but yeah, we can run an optimizer to do the exact thing that I was going to do manually. We'll run it for, say, 200 or 100 epochs. We'll be generous. And it will go through constantly tweaking and changing the variable. And we'll finally display out our final model. Let's fit it some more. It needs some more time. Okay, what have we got now? Close enough. Okay, so it's went through, it's tweaked and changed the variable until it's fit the curve to my shot. Now I'll just look at the variable. So if I go to my angle shot, angle variable dot numpy. Numpy, there we go. 63 degrees is the angle of my shot. The force behind my shot is 123. Does anybody know what 123 means? Anybody want to take a guess? I mean, logically, it should be like a reasonable metric of force. However, I haven't scaled the image when I put it in. It's just measuring the pixels. So what's very nice is it tells me how many pixels of force I'm throwing the ball. So if this was like if this image was to scale and I did throw the ball, say, a kilometer, this would be 123 meters per second. But because I didn't scale the image, it's 123 pixels per second, which is useful. But we'll just ignore it. I'm mainly focused on the angle. And why am I mainly focused on the angle? Good question. Here's an animation of the fitting that just happened. I usually, when I show this, I'm usually showing this to people who haven't done machine learning or worked with Python or Matplotlib, and they don't appreciate how hard it is to make an animated graph. And so if you do appreciate how hard it is to make an animated graph, you can see all the code to do the animated graph alongside fitting a model while showing the model fitting to the graph. So there's the link to all that. That's all in like a collab. Oh, thank you. Oh, thank you. Thank you. That is the first time anyone's ever clapped for this, but I love it. I love it. OK, cool. Thank you. This is the question I get asked a lot. So I've done all this. I've worked out the angle of my shot. But I don't know what to do with it. So what I'm going to do is what I normally do when I've done something cool and somebody asks me this question is I retroactively make up a use case. So the idea is I went away and I asked my friend who is a basketball semi-pro, and I said, OK, if I want to shoot a ball from this distance on the court, like close up, and I want to move to further away in the court, how do I do it? What do I change about my technique in doing that? And she said, you don't need to change your technique. Your technique should stay the exact same. The only thing that should change is the force behind the ball. So I'm getting nods. Yeah, OK. The force behind the ball should change. So power comes from your legs or anywhere, but the angle of the ball should stay constant. And I thought, excellent. So that gives me a reason of why I've done all this. So if I can work out the angle of all of my shots and work out how consistent I am, in theory, this application that I'm developing could be used to measure how good of a basketball player you are. If you're consistent, in theory, you're good. Yes. OK. So what have I done? If I want to analyze a shot, it's only 6 easy steps. So first of all, to record the shot. Then to cycle home, because I have to do it all on my computer. Trim the video to the exact point where I take my shot. Apply pre-processing. So in the first case, I used the reflective tape on the ball. Turns out that was completely a waste of time. There's actually a pre-processing technique that I've done previously, and I didn't think about it, where I take one frame and subtract it from the next frame, and then only the pixels that have changed remain. And I apply that across multiple frames, and you get like a trail, so you don't need to wrap tape around the ball. Does anybody know what this pre-processing technique is called? OK, I don't either. But what I call it is delta frames. So if you do know the actual word for it, please tell me afterwards, because I've been telling everyone that it's called delta frames. So trim the video, apply these delta frames, go through, crop the shot in, because my model where I fit a curve, it assumes that the start of the shot starts at the origin, so 0, 0. So I need to make sure I crop my shot in. Then run my model that fits the line to the curve. It runs. And then at the very end, I get the angle of my shot. So pretty straightforward. The only thing is that cycling home takes about 10 minutes. Trimming the video, I have to do that manually in Python, which takes about 5 minutes to find the point in the video. The pre-processing is super cheap. That's just a bit of Python code, -1 matrix from the next matrix. Cropping the shot takes about 5 minutes, manually adjusting the parameters and stuff. Running the model, it's about a second to actually fit the model if it starts at reasonable defaults. So the idea is I want to play more basketball. I don't want to have to cycle home. The idea is what can I do to solve this problem? Well, what you usually do to solve problems is you throw neural networks at them. So I'm going to throw a neural network there, and then I'm going to throw a neural network at the cropping of the shot. So then that will automate all the manual steps, and then I can not have to go home and play more basketball. So that's what I'm going to do now. I go through. First thing I do is need to request access. All right. What you would have seen here is just a video of that ghostly image of me shooting a ball. but this is what happens when you share slides across corporate accounts. So yeah, you would have seen a video of me taking shots, and you see just the white outline of me taking the shot. And this is where I would have explained that rather than, first of all, trimming the video to my shot and then running the pre-processing, because the pre-processing, the delta image stuff is so cheap to do, it's just subtracting a matrix from another matrix, I should just do that for all the videos. And it's really unfortunate you can't see the video, because the idea is that I would have showed you, as I'm taking the shot, I could just train an image classifier to say, okay, whenever you see a nice clear arc in my shot, predict that I'm taking a shot. And then if I'm running around or it's all fuzzy and noisy, then just say I'm not making a shot. So it's like a shot or not predictor. So if you see a nice clean arc in the video, it's a shot. If you don't, it's not a shot. So how would I do this? I would go through and I would create a shots model. So yeah, this is, if you see this, it's going to be a nice clean shot. Let's just say yes to a shot. If you see anything else, it's not a shot. Binary classification. Who here's done binary classification? Yes, everyone. All right, the next bit, so the data. So this is, I usually don't go into the detail I'm about to go into, because to collect data for this, I just recorded myself taking a shot, and I knew I had to label the data, so that created this kind of negative feedback that I didn't want to collect a lot of data. So I recorded one session of me taking a shot, approximately 5 minutes of video. And so I needed to augment the data. I needed to kind of get more data from the data I collected. And so I've got a notebook here that shows how I just took each image, translated it like 5 pixels to the left, 5 pixels up and down. Who here's ever heard of like data augmentation with images? Yeah, it's like quite like a common thing to do. I didn't need to do that, because it turns out Keras actually has that built in now. So good thing to note is if you're ever doing image classification in Keras, there's actually just a generator here, and you can say, here's my data. I'm going to feed it into my model. It's going to automatically augment your model by twisting it and doing even more stuff like color changes and brightness changes. So that was a bit of a time wasted when I did that. The next portion is how, after I built my model, okay, what is the code I used for my model? So I used Keras to train the model. The actual model structure I borrowed from the mnist example. So who here's heard of the mnist handwritten digits? Yeah, it's like the hello world of image recognition. So Keras has a really good example on their GitHub of model structure that trains for the mnist really well. Mnist is detecting curves and lines, so I figured mine's kind of a curvy line. So find an application that does something similar and look at what they did for inspiration. The only main thing to note is in their version of the model, they're doing a multi-classification. I just care about if it's yes or no, so I just got to make sure that it's the output is a one node and a single sigmoid activation. So that's going to give me a binary classifier. Onto how do I actually bring this model to the basketball court? Who here's productionized a machine learning model? A lot fewer people than people who say they do machine learning. So it's a tricky thing, productionizing machine learning models. The most fun tool I found, being previously a web developer, I started using TensorFlow.js. Who here's heard of TensorFlow.js? A couple of people. Okay, so TensorFlow.js is a TensorFlow library that runs in JavaScript, as the name suggests. What's really cool about it is it actually has a slightly, it's nice, it's got a slightly different API than the normal TensorFlow API. It's actually got quite a few better high-level APIs. So it's got things like a little line of code that will take an image and feed it directly into your machine learning algorithm, like it will do the transformations for you. And it also has an API that just takes Keras models and converts them into TensorFlow.js models and allows you to just run them in the browser. So it's incredibly useful. For this application, it's perfect because I've got some TensorFlow models, or I've got some Keras models. And here is the first one. So we've got my shot or not application. I've built the Keras model, and I've got the output here being shown, all in real time. So this is all actually running in my browser. And you can see, as I shoot, I'm doing the calculation of the delta image, all in the browser as well. And you see it spikes up when I shoot. So that's it. There's also a little button down here that says camera. And what's nice about this is, I don't know if everyone ever tried to build camera applications. So this is very overfit to basketball courts. But the closest thing we have, so we have the closest thing to a basketball, which is a loaf of bread. So it's a very overfit model. It's so overfit, it only knows when I'm shooting from this side of the screen. So you can see where it needs improving. So I'm going to attempt to, it's such a good model. I'm going to attempt, it needs to also think that I'm running around. I didn't train it on blank images. Like, here we go. I'm going to throw it up there. I need to imagine where the basket is. Okay. Hey, there we go. We got a spy. Thank you very much. All right, there's the shot or not model available on my GitHub. What's actually kind of cool about that, because it's all TensorFlow JS, it's all running in JavaScript. My productionization platform is just the GitHub pages. So if you actually go to the GitHub repo, there's a link, and it's all running from GitHub pages. So yeah, you can productionize machine learning in GitHub. Let's move on. So I know when I'm taking a shot or not. The idea is now I want to crop in where I'm taking my shot from. I could do an image-to-image model. That's a bit crazy to do that. I could simplify it by saying, okay, if I just know where to crop it from, that's useful, and I can do the rest of the cropping in code. So I could just imagine, yeah, x and y axis. Just tell me where my shot is taken from. So I need to predict two numbers, the x coordinate and the y coordinate of the base of the shot. And I can just in code say, okay, crop from this position. And the auto cropping model then is not a classification model, it's actually just a regression model. And yeah, where's the shot? Predict me two numbers though, not just a single number, yeah, 2 for x and y. And yeah, this is the way it's going to be applied. I didn't actually know this when I built it. It is apparently called multi-target regression. So yeah, good thing to note. Moving on, where to crop it from. This is the data. I did also do this sort of time-wasting thing of writing my own code to augment the data set, left, right, up, down. Although in this case, it wasn't entirely wasted, because if I were to do it through the Keras API, I need to also augment the Y output in this case. So if I translate my image to the left, 5 pixels, I need to also translate the Y output to the left, which I don't believe the Keras API supports. If anybody knows any kind of data augmentation tools that do this, please tell me afterwards, because this was very hard to do. The actual shot, the exact same as before, because it's predicting with the same input data. I don't see why I needed to change the model at all. The only thing I needed to change the model was the output. So because I'm predicting two numbers, it's going to be 2 nodes and a linear activation. That's going to give me 2 regression outputs. And moving swiftly on, the demo that demos this is similar sort of thing. Very clean UI, as you can see. We're just going to wait for this to load. Here we go. Nope. Waiting for the video to load now. There we go. So we've got the video loading. I've got the output of my shot or not running at the bottom. And I also have the output of my where from model, or the where's the base of the shot happening. You can see it kind of just like doesn't know what to do when I'm not shooting, obviously because it wasn't trained on data of when I was not shooting. It was only trained on data when I was actually making a shot. So it only knows what to do when it sees that nice clean arc. And you can see it kind of gets a bit confused. And then as soon as I make a shot, it kind of jumps into action. I didn't add the use camera function to this just to save myself a bit of embarrassment. But that is both those models running in real time in the browser as well. And you can see I've got the frame rate here. So it's about 50, 60 FPS. What's pretty cool about TensorFlow JS is that it's using OpenGL under the hood. So whatever device you're using, it's going to try to use any kind of graphical acceleration that the device has to run these inferences a lot faster. So there's those 2 models running. The final thing is now to bring it all together. So I've got the trimming of the video happening as a Keras model that I built and productionized in TensorFlow JS. The cropping of the shot, again, built in Keras, productionized in TensorFlow JS. And the code I wrote at the start that actually fit that linear model because the TensorFlow JS library has a kind of carbon copy of the original TensorFlow library, I just reproduced that code that, say, describe a trajectory equation. I just reproduced that in JavaScript in the TensorFlow JavaScript syntax, and that runs the exact same way. So the idea is that I'll feed it an image. It will say, okay, am I making a shot? If I am, okay, where am I making the shot from? Okay, cool. Crop that and run my linear model to fit this line. And then I just pluck out the two variables that it's optimized, so the angle and the force. And it all runs inside a web page. And here is the final demo. Hopefully it loads in a reasonable hour. Here we go, here we go. All right, so I've got, I know, exciting. I've got the video at the top running. You'll see a little flash of a cross. That's the where model running. And you see down here where it produces the data. So this is the cropping of the data at the bottom. And then I click this little checkbox. And it's going to run the model as well to fit. Boom. So there we go. So the angle of that shot there was 52 degrees. Let's see how consistent I am. Professionals are within 1 degree of each shot. 57. So I'm not a professional. And now I know that. That is the entire demo. 53 again, yeah, not good. That is the entire demo. Thank you all so much for listening. Here's my Twitter and blah blah blah. Yeah. Thank you.
I have a lot of questions.
Yeah, me too.
Does anybody have a question for Zack? Come on. There's a microphone on the seat in front of you.
Oh, there is? Oh, wow.
Yeah?
Hello. Yeah. Hello.
Yep.
Okay, nice. Yeah, just a small. You were asking, is it linear regression? It's.
That might be me. That's fine. Yeah, go on.
Yeah, the first trajectory equation.
Yeah.
It's. Just Google. It's not linear. It's polynomial regression. So
It's polynomial.
yeah. So there are numbers.
Whew, that's a load off my chest. Okay, polynomial regression.
Any question for Zack? Yeah?
Did it help you get any better at basketball?
So, interestingly enough, after I finished building this, I was already bored of basketball. So, I'm moving on to new grounds.
Any other question?
Hi. I really appreciate you create this. So would you use it to try to help yourself improving the technique of shooting the basketball?
So that's a good question. So the idea is that this app I came up with the use case halfway through building it. The idea was that so long as it can measure how consistent I am, it's less of helping me improve and more just keeping track of how well I'm improving. Because the idea is that if you're consistent at shooting, then you're a better basketball player. So yeah, it's less about improving your shot and more just tracking your progress.
Any other question? Yeah, over there.
As you're capturing the trajectory in 2D, so I guess you have to rely on the camera fixed at a certain
Yeah,
angle
yeah.
to capture that. Have you thought about 3D model?
So I have.
Can you repeat the question?
Oh yes. So the question was, I was capturing the shot in just a 2D flat image, and is there an option to potentially, if the camera was positioned differently, to capture a shot from three-dimensional space, or like considering the three-dimensional space of the shot? So the idea is that if you're able to, because as soon as you change the angle, I was very careful to stay like perfectly flat to it to make my life as easy as possible. As soon as you move like in a different angle, the trajectory equation won't fit anymore. Because the trajectory equation only applies to like a two-dimensional trajectory. I'm sure there's definitely a trajectory equation for a three-dimensional trajectory that's then sort of, I don't know what you call it, like projected onto a two-dimensional plane. so long as you encode that in the TensorFlow model, it should be able to fit it. So whatever special new angle that you start shooting the ball at, as long as you find an equation that describes the new curve, you should be able to just encode it in TensorFlow and it should just work. It should do.
Sounds good.
Yeah.
Thinking about extension like to 3D, because like then you have to rely on, you have to be like perpendicular to your.
Yeah. It's definitely one of the many downsides of this application. Oh yeah, at the back.
Have you tried to use just regular scikit-learn for the trajectory curve fitting rather than TensorFlow, or it just felt like using TensorFlow because it was fun?
So I didn't use TensorFlow because it was fun. What do you use scikit-learn for that? I couldn't find it. I didn't know because the idea was I wanted to find the angle of my shot, and I could fit just like a I don't know, like a neural network model or a more advanced polynomial model. I don't know how to make custom polynomials in scikit-learn, so that was the reason why. Actually, do I? I don't know. I didn't think about it long enough. So no, I chose TensorFlow because I thought that was the right solution. But now that I'm thinking about it, maybe I didn't have to use TensorFlow.
Or a follow-up to that, what about like an end-to-end model that does, like one neural network that does the whole thing, end-to-end?
That would require a lot of training data, I feel, and I would have to label the training data. But I had considered that, like maybe cutting out some of the steps and maybe just have one neural network model that tells me the angle. Actually, I could use this current model to take some data and produce those labels and then train that into another neural network model. So that would be a good next step. Yeah, I could use this for the labeling collection. Yeah, it's a good idea. Yeah, at the back.
Hello? Yeah, right. So, yeah, I just had this thought where if you're really close to the net, your angle does have to change because you can't make it with the same angle.
Oh, yeah.
Did you manage to find like a distance where that kind of rule worked, where keeping the angle the same?
So the question was, when you get close to the net, then you do need to change your angle. It doesn't apply anymore. I didn't consider all the edge cases for this. The idea was the free throw shooting. That's like one of the main metrics of basketball, like how good you are from the free throw line, and in that sort of area. So yes, I didn't consider the edge cases of the layups, I believe they're called. Yep.
Can this model be connected with some, I don't know, mobile basketball game? So you will be playing in real life and playing on the screen in game.
So in theory, it could, because it's just running on the web browser, and you can add in any kind of gamification you want. I'm trying to think. I can't. So like every time I tell people just in person that I built this basketball app, and they say, "Oh, does it tell you when you make a shot?" I'm like, "No, but that would have been much better." It can tell you the exact angle of your shot, though. I can't think of a game that does that. I was thinking, because there's a database online that tells you the exact angle of every professional basketballer's shots. And I was thinking maybe you can play, and it can tell you not the angle that you shoot at, but who do you shoot like. So it's like, yeah, which could be cool. Or you have to, I don't know. I honestly don't know. It was a very, very not thought through application. Yeah.
Can you hear? Okay. So I have a question with respect to your negative sampling.
Pardon?
Negative sampling. The way how you sample negatives instance.
The sampling?
Yeah.
Okay.
The one with hoops and the one without hoops. So if you sample like all the without hoops, like close to 62 degrees, would that be more difficult to train the models?
So the question was, I sampled the shot or not, the hoops or not hoops. Did you say in the city?
No, I mean in the degree, like close to 60. 60.
Close to 60 degrees.
Close to 60 degrees. Oh yeah, so there's it is very overfit. I will admit that. For example, you could see also it especially shows in the where I'm shooting from model, because when I'm not doing anything, it's drifting towards the right hand side of the screen. With the shot or not, I try to augment the data as much as possible, and most of my shots were between 60 and 70 degrees. So I haven't tested it with data outside of those ranges. So it is almost definitely overfit to where I'm shooting from. And more to that, also the model that I train at the end, I set the default values of the line that gets fit to close to 60 and 70. And yeah, I cheated a lot in getting this to work. Yeah. Ooh. I don't know. There is data around basketballers' heights and the angles that they shoot at, and there is apparently an optimal, like there's a theoretical optimal angle of a shot to make the basketball appear as wide as possible, and yeah, there's a lot of stuff around that. So there's probably an answer to that question, but I don't have it. Sorry. That's good. So the idea is that this is, if you already know the height of the person, what is the optimal angle they should be shooting at? That is probably true. And I guess the idea is this application will tell you what you're currently shooting at, and you can use both of those metrics to try to fit it together. So yeah, that's a good attachment to the app. Be like, oh, you should be shooting at this angle, shoot at a higher angle. Actually, that would help improve. So that would actually make the application useful. No, but yeah. So that's actually I should definitely add that, because that would actually make it. You could see how much you should change your angle by. So yeah, that's a good thing. Thank you.
All right, let's wrap it up.
All right, thank you very much.
Stands up.
Thank you.